Hello, can you hear me? Can you see my screen? Someone's there. Someone from the organization could come on, please. Hello? There is someone there, please. Oh, okay. I just see here in the chat that you can hear me. Awesome. Yeah, it would be nice if someone from the organization sometimes show up here to say uh, something, okay? Okay, I'm gonna share again. Here we go. Well, so first of all, thank you for inviting to be here. I really like uh, to have this moment with students and be part of these projects to help uh, actually sharing about phenomics. So thank you a lot for this opportunity. Uh, the main goal here today is to talk about phenomics and different applications on plant breeding, but also giving some concepts on how to use phenomics on plant breeding. But at the beginning, let's go first to start with some concepts and actually basic concepts. And the first basic concept that is important to start here is to talk about what it is electromagnetic spectrum, which is this range. Let me just put this here. It is this range of different frequencies or radiations that we have in the spectrum. But basically, all type of radiations come from a source. In our case, is the sun, and this radiation travels everywhere in what we call waves, right? And the first, and this radiation also can be classified as the wavelength, which is the distance between the peak of one wave to another one, and also the number of waves in a period of time, which what we call frequency. And based on those characteristics, scientists actually they classified the radiation in some regions. For example, here there is the first one called radio, where we have a long wavelength and lower frequency. And then we have the microwave. The microwave is a little bit shorter than the radio, and the microwave we normally use for cell phones and also the microwave machine, right, to warm food. The radio has this long wavelength that has the ability to go over buildings, go mountains, so go really far. Uh, uh, that's why we, for example, use the radio for listen songs. Infrared and visible region are regions that we're going to talk later. It's very important for plants. And a little bit shorter, we have the ultraviolet, the X-ray. X-ray actually, as you can see here, has smaller wavelength and high frequency because you have more waves in a period of time. X-ray has the ability to pass tissues, but not dense tissues as bones. That's why, for example, we use X-ray on medicine. In plants, we have been using X-ray to investigate roots and also to investigate seeds quality. to see if there is any type of problem internal in the seed. And then we have the gamma ray, which is really high frequency and very short wavelength. And the gamma ray has this ability to, in plant breeding, actually, it's used for cause mutation, and with these other, promote other um, variability for selection. So, as I mentioned before, we have the sun, our main source for radiation. All these type of radiations come from the source to our main object, in our case, our plants, right? As we saw also in the previous slide, we have many different type of radiations, and once that this radiation come to the surface, in our case is the plant, all these type of reactions can happen. We can suffer transmission, reflection, refraction, diffraction when we, broke the radiation in many different directions, absorption, right, by the tissues here, and also scattering. If we amplify our surface, right, so we're gonna see internally in this object that the radiation is coming to the surface, and according to the morphology internally in this surface, the reactions, those reactions that we just mentioned, is going to be different. For example, imagine a plant with many more trichomes here, right? So these structures here in the leaf. The way that the light or the radiation is going to reflect or react to these more trichomes is going to be different. And another point is, like, imagine that we have more water content or less chlorophyll. So the way that the radiation is going to react also is going to be different. The main point is we're going to use, doesn't matter what we have here, we're going to use sensors. In our case, it's going to be, for example, drones, to collect the radiation that turns back and try to and we're going to use that information to try to explain our biological question. Okay, so in a general view is what we're going to do. We have the source of radiation. This radiation come to the surface. All these reactions going to happen according to the surface. That can be a different genotype, that can be a different plant or object, but doesn't matter with the surface here. Those reactions gonna be different, and we're gonna use our sensor to capture. Okay, and with this we have another concept called reflectance, which is gonna be the fraction of incident radiation, right? So the fraction of incident radiation that turns back in our sensors capturing. Okay, so is this proportion of radiation that is reflecting back and being captured. All right. So let's see here. Just let me check the chat if there is any. Oh, can can you are you guys still seeing my presentation? Please comment there just to see if we are able to. Hello? Okay. Okay, I'm gonna continue here. All right. So let's continue. Uh, for example, This idea can be used for example, to uh, first of all, let's understand this graphic initially. On the x-axis here, we have wavelength. We already mentioned, which it is the distance between the peak of two waves. And the y-axis here, we have the reflectance, the proportion of the light that is incident in the object that turns back in the sensor capture. As you can see, if the snow has higher reflectance on the visible region, right? And that goes down when we go towards the infrared. The dry soil start very low reflectance and then goes a little bit up, right, towards the infrared. But the most important point here in our case is the vegetation profile, reflectance profile. We have high absorption on the blue, we have a little peak on the green, and then high absorption on the red. And then we have a slope in the red edge before we going towards the NIR. Okay, so the vegetation always gonna have this shape, and however, besides the vegetation have the same shape or profile, right? Reflectance profile, the amount of reflectance along the spectrum is gonna be different across crops. As you can see, rice, sugarcane, other crops, they have different profile. They have the same profile, reflectance profile, right? The shape. However, the amount along the spectrum is going to be different. And then we can use these reflectance quantities to classify different vegetations or different crops or, plant species. The same idea here also can be used for differentiate genotypes in a breeding population. For example, imagine here we have, for example, a wheat population, right? And then we have a very light green plant. Let's suppose that this plant's healthy and still very greenish. And then, as you can see, there is this lower or higher absorption on the red and higher reflectance on the NIR. On the other side, for example, imagine this other genotype, which probably is early maturity or is already, in senescence or have some disease, has a little bit higher reflectance on the red and very low reflectance on the NIR compared to the other genotype. These regions is highly related with water content. And then we can see, for example, here some stress or senescence in the plants. We can use this for then apply selection on breeding. Uh, this, if we go a little bit further, right, we also are able, for example, to differentiate morphological parts in a plant. For example, we have here hyperspectral information, right? Probably at this point in your course, you guys already saw some different type of sensors, but this is a hyperspectral. So each one of those gray squares or gray images is one different wavelength in the spectrum that is being captured. And for example, basically in this project here, the researchers select pixels that represent the leaves, pixels that represent the stalk, the panicle, and the background. And when they plot those reflectance profiles, right? So here's the same graphic, wavelength and reflectance. And when they plot those on the graphic, they were able to see that different morphological parts also has different, amount of reflectance along the spectrum. And that idea can be used, for example, for applying semantic segmentation, which is basically simplifying the image on clusters. As you can see, once that you train the model to recognize the profile, the model are able to answer back showing what supposed to be leaves, stalk, or panicle. And with some computer computer programming, it's possible to use those segmented parts to collect extra information. For example, the height of the last leaf, the panicle height, the panicle within plant height, and many other measurements that would be very time consuming to collect in other situations. Once that you already have, for example, a model trained for one crop, you also can adapt the same model for a different crop or related crop. In this case, the model were trained for sorghum, and the authors try to adapt the same model for evaluating corn. Of course, the adaptation is not going to be very, straightforward, because those models, machine learning models, they also need training, right? Because the model never saw corn before, is having some issues on, you know, identifying those. But you can include extra information there and improve the model accuracy over time with more and more information with corn. But the good point here is you already have something to start, right? So that's a good way to do it. Okay. So for uh, the first part on very basic concepts that I have was these. I'm just gonna check the chat to see if we have any question there. Let me see. Um, let me see if you guys have questions. No? Oh, the slide's not showing. Now you have stopped sharing. Please share again. Mhm. Okay. Could you you can see my slide. Mm. Can you see it now? Someone from the organization need to share it. Can you see it? Are you seeing my slides? Uh, should I continue? Mhm. Okay, I'm gonna continue with the other slides. Okay, so um, I ask for someone from that is organizing there to try to figure what's going on. Right. So that was what we have for basic and basic information. Let's see about high throughput phenotyping platforms. When we talk about high throughput phenotyping platforms, the first concept that we really need to understand is remote sensing. And basically, it is important to understand here that remote sensing is basically, in a simple way, is collecting information without touching it, without physical contact. So you're collecting information and make one decision without physical contact. And there are two type of uh, man sensors, active and passive sensor. Uh, The active sensors, they have the ability to emit the signal and also collect the same signal. For instance, we have radar and lidar as uh, examples. A good way to understand this is how the bats move around, right? So the bats, they produce the signal, and when the signal have contact with the surface and turns back, the bats can capture this information and map where to fly or where to go. But in general, the majority of sensors that we're gonna have are those called passive sensors, and the passive sensors is more common and cheaper, and we have the RGB, the multispectral, and the hyperspectral. In a general point of view, the RGB is gonna cover the blue, the red, and the blue, the green, and the red region, which it comes from 400 to 700 nanometers. We are talking about nanometers is the distance between the peak of one wave to another wave, right? So those are the RGB region where we're gonna collect images, and also when we go to the multispectral, we have the RGB. Normally, we have one wavelength here on the red edge and another wavelength on the NIR. The hyperspectral, on the other hand, is going to cover the whole spectrum, considering the visible region and the NIR region, the infrared region. Okay. Basically, those sensors every 10, 15, 20 wavelength, we're gonna have one, filter or one sensor capture information there. That's why with the hyperspectral, we can build those profiles that we can see here. For example, each line here or each color that you guys see is one different genotype in a potato population. That's how they perform. Okay. And when we talk about phenotyping platforms, is the combination between the sensor that we just saw, RGB, multispectral, hyperspectral, LiDAR, or LiDAR, for example, combined in a platform. And this platform can be a vehicle or a system to hold the sensor. This platform can be ground-based. The ground-based, for example, in this specific case, we call this, it's like a chain, actually, but basically the sensor is fixed here, and there is this platform that's gonna bring the plant to be to suffer imagery, right? So to collect data from the greenhouse, for example, all the way to the sensor. We have the system called gantry, where the plant's still fixed and the sensor actually moves. We have the suspension system, where the sensor move on these, axis, predefined axis. So we need to plan our experiment in a way that the sensor can cover. We can fix the sensor in a vehicle. In this case, is a tractor. So the platform is moving and the plant is still fixed. Or even in robots, also is another way to do it. When we talk about air-based platforms, we have drones, which is the cheapest or the low-cost systems that we have. And the more common, because we can cover more space with lower investment in general. Or airplanes, right? So depending of the sensor is going to be very heavy, and you require airplane for using, collecting those images. And also we have the space-based platforms, which basically, for example, as you can see here, are sensors on satellites. Okay. This is one location in Varningen where, for example, we can have, just let me see here. Mm. This is where we can have, is a university, right? And they have this system there where we have all those phenotyping platforms in one location. As you can see here, they have the system where the plants come directly from the greenhouse to be phenotyped and suffer, pass for imagery in a box. Also, they have a gantry system that move the sensor above the plants and so on. That's a very interesting place. If you guys have I hardly recommend inviting someone from this university to talk with you about this project. It's very interesting. Another system, it is this one at the University of Arizona, along with uh, USDA arid lands. Okay,
Hello,
arid
Dr.
lands.
Felipe.
Uh, in this specific case, this station, actually, this system, phenotyping platform, were in a desert, Maricopa Desert, and was very interesting to see that they were growing and planting lettuce there. That was very interesting. So basically, this is a huge box with all those type of sensors, and as you can see, this platform goes down, and they can collecting images on the in the plants below. That was very interesting to see, and also I also recommend you guys go in this web page, TerraRef, right? And contact someone there to talk with you guys and bring more information. That's a very interesting project. This station also develop different other type of phenotyping platforms, as you can see here. And they were adapting, for example, bicycles or other machinery in the farm and including sensors on those to collect information, to use for phenotyping. And of course, robots and also drones. When we see end-to-end on the crop growth, right? For each moment, we have a recommendation for platform and sensor. For example, at the beginning, when we are evaluating the soil for planting, we can use soil conductivity sensors to map, for example, pH in the soil. On early stages, we have more problem with weeds, with detection, right? For instance, we can use a hyperspectral sensor or RGB sensor connect to a drone to have a better view and map the regions where we have weeds. On early growth, we have nutrient status assessment, mainly nitrogen, which is also can be captured using a soil or a ground platform. In this case, here is a tractor or drones, or when we think in large scale, like farms area, we can use satellites as well. Then we have uh, abiotic, right? Abiotic stress and biotic stress. For those, we can use a thermal camera. Thermal is very related with, stress, and also hyperspectrum. Here, the recommendation is to use drones because you're gonna be very close to the plant to really assess the stress that the plant's going on, the plants is having. Another point here is, for example, predicting yield, and then for prediction yield, we can use a multispectral sensor to calculate vegetation weights to be very related with the production, and then we have drones for experiments and satellites for farmers areas. Okay, the the lodging detection we can use a drone in a RGB. The lodging here can be calculated using, for example, the digital surface model, which is one output from the orthomosaic step, or even you can train machine learning models to recognize patterns of lodging. So those are two possibilities how to do it. And of course, when you are harvesting, right? So on the combine, we have sensors that can give us yield mapping as well for harvesting. This is another paper that I really recommend you guys to read because there are many concepts there. It's very easy to understand, and I guess gonna help to really memorize or understand how we have been using phenomics for data collection on agriculture in general, but also plant breeding. Okay. Well, so uh, let me see if you guys have questions. Just let me check back here. Okay, no questions. Mhm. So please go typing the questions there. Okay. All right. So let's continue here. To talk about phenomics applications, first of all, the phenomics concept is very important. For example, when you um, are deciding to use or not phenomics, it's important to see if the new method is reducing costs, time, improving the labor quality of life, or reducing the risks of having someone in the field, and also improve data quality. The secret here is if your new method to use digital phenotyping is improving at least two of those four topics, you are good to go. So basically here the idea is changing the ways of work. So traditionally I have been going to the field walking or doing collecting data in manually in a specific way. And now our goal is to do this digitally. So I and with these I'm collecting faster, or I'm reducing costs for people going to the field, or I'm reducing the risk of exposing this person for some accident in the field, and also improving the pattern and the data quality there. So all those four topics must be evaluated before changing the method. Okay. What I'm going to present is everything that I talk here, and also I'm going to present is from my previous experience on at University of Wisconsin and also North Dakota State University, work with potatoes and wheat mainly. Okay. The first application actually is stand count. Stand count is very simple to do, but it's very important to have in mind that you have a very short window for data collection, uh, which is going to happen in this stage. So before the plants start touching each other. For example, let's see here. At 36 days after planting, when we go to the field there, we collect those images, right? So we can see here that 36 days we are able to see those plants sprouting from the field. However, the blue genotype here didn't show yet. In the next week, the first genotypes are already all connected. I mean, all plants touching each other, and then the blue genotype is ready to go, right? So what's happening is when we are doing this type of evaluation, sometimes you need to do more than one flight to count correctly the plants. When you have in your population genotypes that has very different growing stages. For example, we have uh, early genotypes and late genotypes happening at the same time. That's very common on crops that are less selected or population with less selection pressure, where we have this combination of early genotypes, those genotypes that really sprout very fast, and late genotypes, those genotypes that take a while to germinate, right? So in breeding population, those are very common. Okay. But the point here is, as you can see, the plants, when the plants start touching each other, the algorithm or the computer has more difficulty to understand what is a plant or not. So starting counting things in a wrong way. So it's very important to keep in mind that we should choose a specific moment when the plants are not touching each other. All right. For example, for corn, soybeans, sunflower, other crops, they are more standard. So all genotypes they come, you know, almost at the same time, right? They're gonna germinate almost at the same time and sprout right from the soil, almost at the same time. And we do not have this problem. However, for example, in potatoes, where the population is really segregating for germination, we're gonna have to make more than one flight um, every week. Okay. Uh, Another point that you also can do here, we are using segmentation, but here what you can do is train a machine learning model, for example, to identify and count objects. And this is a little bit more harder at the beginning to do it. However, the quality of results is going to be way better when you have a well-trained model. This is just one example in cassava. Okay. The same idea here you also can use, for example, to count seeds in a year, to count pollen, and also to count animals, as you can see here. Basically the point is like segmenting the background and highlight the objects that you want to count. And then you can apply the algorithms or available algorithms to count it. Okay. Another important application is to talk about healthiness or relative maturity. For instance, the most used phenomics trait is uh, what we call vegetation indices. Here's one example, for example, NDVI, where we have the vegetation index basically is an equation or a formula that has a biological meaning. So you use different parts of the spectrum that we already mentioned, right? So different parts of the spectrum and use those information, right, to calculate a number that has a biological meaning. In other words, as you can see here in DVI, it is a normalization of between NIR and red, spectrums. And for example, when the plant's very green and healthy, is having higher absorption of red color and higher reflectance on the NIR. So reflecting more NIR and reflecting less red. And when you combine those information together, you're gonna have a higher number than when the plant is dying or it's already in senescence, where because you have less chlorophyll, you are not having lower absorption of red, and that then you can increase. Then you're gonna the consequence is increasing the reflectance on red, and also maybe you have the plant has less water content, and also that cause lower reflectance on the NIR. Is the opposite there, right? So we use those information to give us a number that has a biological meaning. In this case, is highly related with greenness. When we go and then here, what we are seeing is when we are scoring plants or genotypes in a population for maturity, we go there and give scores from 1 when the plant's all dead is already dead, right? All the way to 9 when the plant's still green and flowering. Once that this trait is directly related with color or greenness, we can use those equations to give, besides giving visual scores, because uh, humans has different sensors. For example, my sensors, my eyes, see the green color different from your sensors, your eyes. When we use a drone to do it, we have more standard way to collect those information. And as you can see here, we're gonna be more precisely on uh, getting the right standard and comparison between genotypes. Okay. Uh, this is a very nice paper showing how to do it for soybeans, for example. Uh, this paper basically show how the pipeline would be. You start by collecting the images using UAVs, right? And then you create the orthomosaic, and then you're gonna create the grid shape file, which is the plot identification. And from this time, you're gonna collect many flights following the plants from when it's green all the way when the plant is dead, trying to calculate a system, as you can see here, trying to calculate a system to find which time or which flight here is going to be our decision for senescence. Okay, from this point, we already consider the plant as the plant is senescent. And for instance, this paper, they suggest a way to calculate that greenness reduction and find a specific point where you're gonna say, from this point on, I can say the soybean is senescence, okay? And is already mature. That's very interesting way to do it. Okay, so I also recommend reading this paper when you guys have time. Our third case is to talk about plant height and lodging. There is a couple different ways to calculate it, but the one that I think that is easier and to understand and use is to use the digital surface model. Probably you guys already have a class showing how to create orthomosaics, and one output from the creation of our RGB orthomosaic is also having the digital surface model, which basically you have on which basically you have here on the x-axis the longitude, the y-axis the latitude, and each pixel in this image or matrix is gonna be the altitude. When you collect the image only from the soil base and then the same image with plants there and make the subtraction, for example, subtract the altitude with no plants from the altitude with plants, what we have here is what we call canopy height model, which is a model to evaluate canopy. For example, as you can see, initially we have here around 331 meters, right, on both images. And after making the subtraction, we come here for around 30 centimeters, right? Which is the reality of this potato stage of, this potato growth stage. And as you can see, the soil location tends to come around zero. We're supposed to really be around zero. Uh, then what we do, we apply a mask to only select pixels with plants, and then we extract the average height per plot. And this height we can compare and provide breeding select, provide information for breeders and to make selection. You may ask why we can use, for example, only one flight with the plants to collect this information. As you can see, all this green area here, right? So more green, dark green color. It is way higher than this upper part. So if we extract directly the information from one flight, we may are saying that those plants that that we are seeing here are like way taller than the ones that we have, on the lower part of the terrain. But this is just, inclination or terrain problem, not necessarily related with the genotype. So we need to keep this in mind. Okay. And right here we have just a view For example, 40 this potato population, right? So at 40 days after planting, you can see here these little peaks on height that is related with the potatoes, right? Where we have potatoes. And 70 days after plants, you can see where how it looks like. And the interesting part is like, look, these genotypes, those 2 or 3 genotypes that we have right here, they still being the lower height at 70 days. So that can be something related with the genetics or also with some problem in the soil in this location. That's why it's important to have experiment design to really calculate this well. Okay. But experiment design is going to be something that we can talk in another opportunity. The most important point here is to see that it's possible to calculate plant height using output from the orthomosaicing process that you guys probably already saw it. Okay. This is another point. For example, we can calculate lodging based on this altitude, based on those the same system that we just mentioned. Now you also can calculate lodging and comparing how the plants were the height the digital height the plants have before a lodging event and the digital height after a lodging event. For example, here we have all plants green and straight, right? Standing in the right way. And then after some time, we have a very windy day, and then many of those genotype suffer lodging. And that's quite clear when we are using the digital surface model. It's very easy to see the plants that lodged along the way. All right. So those are some examples for the time that I have. What is more important here is just to give you guys an idea where to find information and how to start. Uh, this is a very interesting paper also showing how the future looks like for phenomics, where you have sensors all many locations in the field. Those sensors are connected with, uh, turning on or not the irrigation system. Also, the drone are able to map weeds, to map dead or diseased plants that activate, for example, a robot with an arm that are able to go there and remove those weeds or remove those dead plants, right? All this information is connected with the cloud that is with the cloud, and the clouds are connect directly with the cell phone of the breeder or the researcher or the farmer actually that help to facilitate decision making. This is the future, and there are some prototypes happening right now. For example, at Illinois, University of Illinois at Urbana-Champaign, and other institutions as well. However, we always gonna need people in the field, right? So no technology is gonna, exchange completely the need of people going to the field. That's why, for example, you guys are here actually to learn how those technology works, but also to understand how to do in case the technology didn't work as well, because many times the technology is not going to work when you're collecting data and you need to figure a way to do it visually at least. Where to find information? We have many web pages and you know, you know, available resource. The first one that I recommend is checking the Plant Phenome Journal web page. It's very interesting. I really like the papers that are being published there. We have the International Plant Phenotyping Network that has a list of researchers and institutions connected globally to talk about phenomics. The North America Plant Phenotyping Network, and also the group that I have been leading in in these last few years, which is called Phenom Force. The Phenom Force, it is a online platform that provides free training, right? So a library of many different resources on phenomics. Our main goal always is being to empower early career researchers and connect people. Uh, as you can go there on YouTube and search for Phenom Force, you're gonna have many, workshops showing how to really do it, phenomics. Today here I'm presenting more how concepts and ideas is a start for you guys. But in those workshops are around 1 hour and 30 minutes or 2 hours of people really doing data analysis and image analysis using, uh, drones or satellites. Anyway, many different platforms. Okay. With this, I want to say thank you for this opportunity. I wish you guys having uh, some questions and also understood well what we were thinking for what I want to present today. Okay, cool.
Right.
Hope you guys
Thank you so
understood.
much. Okay. You can. Thank you so much, Dr. Felipe. That's really a profound and insightful presentation you did. Sharing your knowledge and expertise in the aspect of crop phenotyping, with digital technology. It's really great. So let me quickly
All right.
see what's to
So feel
entertain
free also
questions.
to contact me on LinkedIn or send message by email. I will be happy to answer and support you guys uh, when necessary. Okay. So thank you for inviting me. I'm very happy to
I
support
don't
you
know.
guys.
Amosat
And
Muslima, if you are still there, you said you have two
oh, there is
questions.
someone with questions there. You can just
Can you
write
drop
it,
them? Can you drop them in the chat box so I can bring
or
them
can
up?
you also can contact me later though. I guess we are having a hard time understanding this platform. I'm not sure if our colleagues from the organization is there, but I wish someone contacting me or saying something.
Alright, no problem. I'm going to drop your LinkedIn
Okay.
profile to the group so that people can reach out to you. They can connect with you from
All
there.
right.
So
So thank you so much for your time and thank you for inviting. Hope you guys
yes,
enjoy it.
yes,
Okay. Bye
yes, yes,
bye.
yes, yes. Yeah, we did. It's really a great time with you. Alright. Okay, we don't have questions, and I think Dr. Felipe has spent so much time here with us. Alright, it's really a great class with him. Though we had some issues, his slides was not showing at some point, and that was due to network. It's fine, so you can do well to reboot the class. So I'm going to follow him up and get this particular slide from him. So I'm going to share that to the group so that we can uh, complement and level up with the sections where he was speaking and the slides were not showing. Yes. So, all right. Thank you very much, everyone. This is actually the last class. It was a great one. So, uh, just to notify you again, your exams actually coming. So it's coming very soon. But I will give an update about this tomorrow in class. So be able to talk extensively about it. Alright, thank you everyone. We've gradually come to the end of this presentation. Thank you so much. Have a great time. See you tomorrow. Bye.